Hi, welcome to a special episode of Operating Systems class. I'm having to travel a little bit, so I'm recording the next few lectures. I'd like to pick up where we finished off at our last in-class meeting. We were talking about encryption, and we were looking at some example programs in Java that do symmetric encryption and uh, cryptographic hash computation. We didn't get a chance to look at the one that does asymmetric encryption. So let's take a quick look at that. These are the samples. Mostly these should be posted. The one I wanted to look at is this RSA encrypt and decrypt. Before we do that, let's take a look at the key. Remember, for symmetric encryption, I just had a key that I kind of made up, but for asymmetric encryption, you're not really going to want to generate a key yourself. The two keys in the key pair have to be connected mathematically. And if we take a look at the private key, this is the one we're going to be using. And you can see it's way bigger than the one we had with symmetric encryption. So a lot more key material is required. If we look at the public side, you can see, well, it's a lot smaller, but even this is a lot bigger than what we had with AES when we were using symmetric encryption. Now, both this and the private key are really made up of multiple fields. So what you're looking at here is an encoding of the key, a way of writing out all those fields together so that each of them can be extracted. And the private key is a little bigger because it has more fields that are part of that encoding. But even the private key, or sorry, even the public one is way bigger than what we had with AES. Let's take a look at the encrypt and decrypt programs. First, RSA encrypt. This one kind of does the same thing. It first opens your key, so it opens the public side of this. I said each of those keys, the public and the private, are encoded using a particular encoding. And that's what I'm using here. This is the standard that it's encoded with. So this will decode that key from an array of bytes. And then kind of like we did with AES, we can call a factory method on key factory to get a key for RSA. And then we can get an instance of a cipher object calling another factory method saying we'd like to use RSA. And then we can tell that cipher we want to encrypt using the public key we just loaded. And now the nice thing is after this, it works kind of like the symmetric algorithm. We've got this cipher object. We can prepare a sequence of bytes any way we want. I read in a message from the user. I turn it into an array of bytes, and then this same method, doFinal, same way we called it with AES, will encrypt the array of bytes we give it, giving us back a resulting array that's the encrypted version of that input. Here I write that out in base64 encoding, and then this example is done. Its good friend RSA decrypt will undo that encryption, so it reads the other part of the key in base64 encoding, and then that gives it, decoding that gives us an array of bytes. And then that key is also represented with a standard way of encoding it, even as a byte array. So this PKCS8 encoding is how that's encoded. So this object can decode that. We get an RSA object. We get an instance of a cipher object that uses RSA. Actually, I misspoke. We get this key as an RSA key. We get a cipher object that uses RSA, and then we tell it, I want you to decrypt using the private key that I just made. We're going to expect the user to copy and paste in the encrypted message, and then we'll decrypt it again, calling this same function. Once we get a cipher object, encrypting and decrypting is pretty easy. The cipher object is like, I mean, it's an object that knows how to encrypt or decrypt with all the stuff you've told it up to this point. So all you have to do is give it an array and it'll apply whatever its encryption or decryption algorithm is to that. So decrypt the message I got from the user. I turn that into a string and try to print it out. And hopefully I'll get the same string I got originally. So let's run RSA encrypt. It will, right after I hit enter, it reads in I think this one was reading the public key. It makes a cipher object and it's ready to encrypt a string. I just have to give it something like testing 1, 2, 3. And here I didn't worry about the length of this message. This encryption object can handle any length of message. It'll pad it as needed if it needs to. And then this is the RSA encrypted version of that input. And you can see this got a lot bigger. Some of that is because I made a much bigger key when I generated this key pair. So encrypting objects gives you an output that's dependent partly on that key size. So let's try the decryption part of this, RSA decrypt. This will automatically read the private part of that key pair. It'll create a cipher object to decrypt that. And all it wants is this string that we just got from the encryption program. So we'll paste that in. When I hit enter, it'll turn that into a byte array. It'll run it through the doFinal method on its cipher object. It'll get a resulting array of bytes. It'll turn that into a string, and we get the same thing that we started with. So this shows that, well, in Java at least, once you've set up your encryption objects, once you've created this cipher object and you've given it the key and told it what to do, you can use it to easily encrypt any array of bytes you want. So we looked at some examples of what we can do with these encryption technologies, or at least, I guess, how to use them. What do you normally do with these? Well, first, a little bit of notation. This will help. This is a standard notation for talking about encryption and decryption. You'll see it in a few places, and it'll make it a little easier to talk about what we want to do with these technologies. Often you'll see encryption written down as a function, E, such that if you give E a key, it'll give you back a function that encrypts with that key. So that's kind of how you can read this. This is a functional notation. E, when given a key, gives you back a function that maps messages to ciphertext messages. And that's really kind of what we saw with the Java API. We prepared a cipher object. When we made that cipher object, or when we initialized it, we gave it a key, and then that cipher object would kind of do this part of the encryption. You could give it any array of bytes, and it would give you ciphertext for that array of bytes. In our notation, since E is a function that goes from a key to an encryption function, if you just said E of some key, that would be talking about the encryption function. And if you took that and applied it to a message, that would be a way of writing down saying ciphertext for this message encrypted with this key. For decryption, we'll use the same kind of notation. We'll think of decryption as a function that when you give it a key, it gives you back a function that decrypts ciphertext. So when you give it a key, it gives you back a function that maps ciphertext back to a plain text message. And this same kind of notation, we could use that for symmetric or asymmetric encryption. Just if we were using symmetric, we'd probably always use the same key to encrypt and decrypt. If we were using asymmetric encryption, we'd have to be clear about what key we were planning to use. If we needed a cryptographic hash, that's even simpler because it doesn't need a key. So H of some message M would be our shorthand notation for a hash of some message M. So we can use this to talk about how we'd use any of these encryption technologies to solve some problems. One problem we might want to worry about, this is one we've kind of ignored up till now, is how do we demonstrate authenticity of a sender? Someone like Plankton here could be sending a message to to Patrick. And if Plankton got Patrick's public key, and the idea is anyone ought to be able to get that key, Plankton could take a message and encrypt it with that key, and yeah, only Patrick could decrypt that. But he can't tell who it came from. So just because it claims to be from Bob doesn't mean it necessarily is. We could to solve this, we need some mechanism for authentication for trying to prove that the sender of a message or the person we're talking with is who they claim to be. In the real world, we often handle this through some kind of attribute of a user. Often you don't need people to prove who they are. You just look at them and you can tell who they are. And we could do the same kind of thing computationally. We could depend on a fingerprint or a retina scan, I guess, to prove that someone is who they say they are. But often in practice, it's a lot easier just to have knowledge that only a particular user would have. And we usually do this in the form of a password. If Patrick can choose, if Bob can choose a password beforehand, and Patrick knows what Bob's password is, then when Bob has to demonstrate that he is who he says he is, he can just show that password. Patrick can check it on a list of passwords, maybe different passwords for each user. And if Bob seems to know his password, then we can decide that Bob is really who he claims to be. The way I'm showing this in this picture, though, is probably a bad idea. I'm kind of making it look like Patrick is the system that Bob is authenticating to. And like Patrick has a list of every user and their password stored somewhere. And that is probably a bad idea because you wouldn't want a big list that just showed everyone's password. In plain text, if an attacker got access to that list, they'd be able to log in not just as one user, but as any of those users. And if a user was lazy and they used the same password across multiple systems, or an attacker might be able to use that to log in somewhere else. So usually we don't store passwords in plain text, and we don't ask people to give us their password, at least not directly, to authenticate themselves. It might be a lot smarter to store the hash of a password. That's what I'm showing down here. Instead of having a list of everyone's password, Patrick could keep a list of cryptographic hashes of their password. And then if you accidentally got that list, you wouldn't actually know anyone's password. In fact, figuring out a password that hashes to that would be computationally hard, at least if you had used a cryptographic hash. And then when Patrick authenticates, he would, I'm getting the names messed up. When Bob authenticates, he would give the hash of that password. Often in computing this hash, you wouldn't just hash the password, but you might mix in maybe some characters from the user's name and even some characters from the system they're authenticating with. And then the hash of the password that got stored would depend on more than just the plain text of the password itself. And that's a good idea because it means just because you compromise one system, you wouldn't necessarily be able to log in to other systems. And it makes it harder to do a dictionary attack, to compute the hash of a bunch of common passwords and then check to see if anyone's using those passwords. So often you'll store a hash that has some other information mixed in. People usually call that a salted password. This system that I've described so far is probably a bad idea as I've described it, because it seems like it's vulnerable to replay attacks. If Bob hashed his password and then sent that hash, well, if that's what he's going to use to authenticate every time, and an eavesdropper could see that, it seems like they could just replay the hash of that password and be able to authenticate without actually knowing the clear text password. A way to fix this is to make it so that when you log in, every time you log in, you're going to have to prove that you know your password without just sending me that password. Every time you log in, you'll have to give me a new proof that you know your password. And a common way to do this is what they'd call challenge handshake or challenge response authentication. To do this, and this is what we're going to do in our last homework assignment, the system you're trying to authenticate with here, Patrick could just generate a random string of bytes and send it to Bob. And then to prove Bob knows his password, Bob could hash that random string of bytes with his password, or with a hash of his password, like I'm showing here, Patrick could get that. If Patrick knows the hash of his password, he could check to see that the hash of Bob's password combined with the random string he just sent out hashes to the same thing that Bob just gave us. But no one could use this, at least no one could reasonably use this to replay Bob's password, because if you came up to Patrick tomorrow and tried to authenticate, you could expect he would send you a different random string of bytes. So knowing the hash that Bob used yesterday wouldn't let you authenticate, wouldn't let you prove that you know the password if you have to hash that with a different random string. A common kind of specific way we do this same kind of thing is using what we'd call one-time use passwords. Here, instead of just agreeing on one password, we could plan ahead for a whole sequence of passwords that Bob's going to have to show. And every time he logs in, he might have to give the next password in the sequence. And then Patrick could keep up with where Bob is in that list. And every time Bob authenticates, he could strike off a password and plan on using the next one. Now here I've shown this as if it's a real list of different passwords that maybe Bob had to come up with in advance. In reality, that's not how you would do this. You'd typically compute a whole sequence of passwords using cryptographic technology. And then for your next password, you could either just compute that, or you could plan ahead and maybe have it printed out on a piece of paper, but you wouldn't have to really come up by yourself with a sequence of passwords, each of which you're only going to use once. But the nice thing about this is every time you log in, you have to show the next password on your sequence. And if someone did get access to your sequence, if they, if you wrote these down and somebody copied one of them, you could tell that that had happened, because the next time you went to log in, you wouldn't be able to use that password because someone else got there before you. So this would also give you a little way of detecting if someone had compromised your list of one-time use passwords. Even with all this stuff, even if you have challenge handshake authentication and you believe that the person who logged in is really who they claim to be, you could still be vulnerable to what's called session hijacking if you wait and let someone authenticate and then you take over their session. Here I'm pretending maybe the Plankton comes along and punches Bob and then takes over his terminal connection. That would be an example of session hijacking, or more typically, this is something you might do in the network if someone authenticated, and then you could somehow get access to a TCP connection they were using. You might be able to send messages over that, taking advantage of the authentication they had already done. This kind of shows us that if we're going to depend on authentication, we probably need some authentication attached to every message we send. We probably don't want to just authenticate once and then depend on that, because maybe somebody could hijack our session after we've done that. Even this crude technique of punching us in the face and sitting down at our chair. So normally we might want to stick a little bit of authentication on every message. Even if you do that, though, you have to be careful that someone can't just take that authentication and copy it to another message. Or maybe another way of saying the same thing is take that message and go in and change parts of it with the authentication still attached. You wouldn't want Plankton to be able to take an authentic message from Bob and modify it and make it still look authentic. So I think the takeaway from this is the authentication needs to somehow cover the contents of the message. Authentication shouldn't be something you can just stick on any message. It should somehow depend on what's in the message. And we'll talk about a standard way of doing that. RSA is kind of nice because even though originally we said, well, you could use this to get secrecy, you would just have to send messages encrypted so only the receiver could decrypt them. And that's easy. You just encrypt them with the receiver's public key. But by itself, that doesn't demonstrate that the message is authentic. It doesn't demonstrate that it came from the person who claims to have sent it, but if we've got key pairs for everyone, we can have both of these things at the same time just by encrypting a message so that only the receiver can read it. So for my picture, only Patrick can read it, and only Bob could have sent it. And that's what I'm showing here, at least for the arrow going in this direction. How about if I take a message and I encrypt it first with Bob's private key? I'm pretending this K sub D, or sorry, Bob sub D is Bob's private key. Now, that's an encryption operation that anyone can undo, because if it's encrypted with Bob's private key, it decrypts with Bob's public key, and anyone can have that. But only Bob could have encrypted a message like that. If Bob's doing a good job keeping his private key private, that's a message, this first part, taking a message, encrypting it with Bob's private key. Anyone can decrypt that, but Bob is the only one who should be able to encrypt a message like that. But anyone could read that message. But how about if I take that? That should be a sequence of bytes. I'll take that and I'll encrypt it again, so only Patrick can read that. Seems like I could take the output of that first encryption and send that as input to an encryption with Patrick's public key. Anyone could encrypt like that, but only Patrick could undo that encryption. So when Patrick gets a message encrypted like this, seems like he could decrypt it using his private key, and then he could encrypt it, he could then decrypt it using Bob's public key. The first part of that is a decryption only Patrick can do. The second part is a encryption only Bob could have done. So this should give us both authenticity, only Patrick could have prepared a message like that, and secrecy, only the holder of only the holder of Patrick's private key can decrypt that message. But almost no one does that, at least not for message after message after message. The reason is asymmetric crypto systems tend to be kind of expensive. So backing up to this slide, every time I send a message, looks like I have to encrypt it twice using an encryption algorithm that's kind of expensive. What could I do that's a little bit cheaper? Well, normally, even if you're using a key pair or two key pairs, like in this example, you don't use that. You don't use those pairs to cover every message you're going to send. Usually, you would use them to establish what's called a session key. A session key is a symmetric key that you're going to use to encrypt all subsequent communication. If you use, so backing up a couple of slides, if you use your asymmetric key to choose a session key and communicate it between the two participants, you can then use that session key to encrypt everything that you send after that, since that session key was sent encrypted by your asymmetric crypto system. Other users shouldn't be able to decrypt it, at least not without a lot of work. But you can generate this session key so that it's a symmetric session key. You can use it with those much cheaper symmetric crypto systems. So even though it'll cost a little bit to pick this key and to share it, all subsequent communication should be cheap. So this is a common trick to get a lot of the advantages of asymmetric encryption, but advantages in terms of what you can do, but a lot of the performance advantages of a symmetric crypto system. Another place, so I think of this as a cryptographic shortcut, because most of the time, after we've agreed to our session key, we're going to use fast, cheap, symmetric encryption to communicate secretly. Another place where I think you see something that looks like a cryptographic shortcut is the way digital signatures work. When we were talking about authenticating every message, or in general, if you want to have a document and you want to mark it as with a digital signature, something shows that it came from you or you agree to it somehow, we want to attach a little bit of cryptographic material to that document that shows that it's authentic, to show that it came from you, or that you agree to that. I guess one simple way we could try to do that is encrypting that document with your private key would be a way of showing that you did that. Because if you take that document and you encrypt it with your private key, anyone can undo that decryption, but only you should have been able to do that. So that would be a way of showing that that message came from you, or at least it went through you. But the problem with this is it'd be kind of expensive. If that was a big document, encrypting that whole thing with your private key is going to be computationally expensive. And after the encryption, it's going to look like any encrypted message. It's going to look like random garbage. It'd be nice if I could stick a demonstration of authenticity on a message without having to turn the message to garbage. And that's really what we expect a digital signature to do. The standard way of doing this, when people talk about a digital signature, they're imagining, or they're using a system that works like this. How about if I take your document and I generate a cryptographic hash of it? The nice thing about this is, even if that's a big document, computing the hash is cheap, and the hash is small. It's just, maybe a couple of hundred bits, even if the document could be a megabyte or more in size. I'll take that cryptographic hash and I'll encrypt that in a way that only the sender, only the signer could do. I'll encrypt it with their private key. And using that notation we talked about a few slides ago, that's what I'm showing here. Take the original document, hash it, and then take that and encrypt it with the private key of whoever's signing that. And like my picture tries to show, just stick that on the end of the document. That should be, a few hundred bits at the end. The rest of the document can still be plain text. It doesn't have to be encrypted. It'll have this little bit of cryptographic material at the end that demonstrates its authenticity. Well, how does it prove that it's authentic? What's to keep someone from doing a message modification attack here? Well, that's what I'm trying to show. How would you do a message modification? Well, how would you try to do this? You could take the signature at the end of a document and you could stick it on the end of another document, or equivalently, you could sneak in and change some parts of that document. But if you did this, if you just tried to move that signature to another document, even a pretty similar document, it would be easy to catch you. And here's how I would do that, or here's how anyone would check that signature. I would take your modified document and I would hash that. And if the cryptographic hash is doing its job, that document, if it's a slightly different document, I would expect it would hash to something different. Remember, the idea of a cryptographic hash is it's really, really, really hard to come up with any other document that hashes to the same thing. So I'll take your modified document, I'll hash it. I can do that because I don't need any key to do that. That'll give me a hash. I'll take the signature at the end and I'll decrypt that. That only requires your public key. And that signature is a tiny little bit of the signed document. So that should be pretty cheap to do. And those hashes shouldn't match. The thing I get from decryption should be the hash of the original message. The thing I get from computing the hash should be the hash of this modified message. And again, if the cryptographic hash is doing its job, those won't match. So this would catch an attacker that was trying to just move the hash to a modified document. These are tricks that are standardly done with encryption. They're kind of, like I've said, one of our most reusable tools for dealing with security risks. And you'll be using them a lot in your last homework assignment. You'll be writing one program that uses a lot of the different techniques that we've talked about. Now, at the start of lecture on Tuesday, I jumped to the encryption stuff because I knew you'd need that for your next homework assignment. We kind of left the we left the protection material halfway done. So let's go back and resume that part. We already did this part. We talked about what protection is. We talked about some of the terminology we'll use in protection. And we were talking about this idea of an access matrix, kind of an imaginary giant two-dimensional table that the OS could use to keep up with all the protection information. We talked about some stuff we'd want to be able to put in this access matrix, essentially the access rights that we'd have if we were a process running in a particular domain trying to access a particular object. We got as far as saying, well, you might not just want to have an access right, you might want some mechanism for giving it away. So we talked about one way we could store that. We could mark access rights. Here we're just using a star to say whether you had that right or you had the ability to give other users or other domains that right. And this could work, but often we avoid this mechanism for giving away rights. And instead, we use a mechanism where it's assumed that every object has one or more owners. And owners have the right to give away anything they want. And that's what I'm trying to show here in this table. Pretend domain D3 is the owner of object O1. So if they were the owner, they could give read or write access to any other domain for that object. Again, here I've just got one owner for that object, but you could have a system where any number of users could be the owner. Often they might call them the administrator for that object, and that means they have the ability to give or take away access rights to other users. And this ends up being more common than having just a special way of marking access rights so you can give them away. Processes, I got this question after class about a week ago. Processes might need to temporarily change their access rights. Like if you were going to do something, if you were going to run some less trusted code, you might want to drop down and remove some access rights, or temporarily, we might need to give you elevated permissions if you were going to use them to do something that you needed to do. So we might want, sorry, I know that was vague. We might want some way of letting processes temporarily change their access rights. And that would usually mean, well, change the domain that they're running in. So to do that, well, we could add some more stuff to this access matrix. We could say, well, if we want to talk about the ability to change domains, then domains also need to be treated as objects. So I've added some columns for domain D2 and D3. And in these columns, I've put some new types of access rights. A switch access right could be used to show that you can switch from the domain for that row, in this case D1, to the domain for that column. So this switch access right says if you're running in domain D1, you can temporarily get the rights of domain D2. And then over here, if you're running in domain D2, you could temporarily get the access rights of domain D3 to let you do things temporarily for which you needed maybe elevated privileges. And control, you can see I marked this one as control. That would mean that this domain is the owner of this other domain, or it decides who can switch into that domain and who can't. So this would give us a flexible way of assigning rights to domains and letting processes temporarily change domains if they need to. This gives us a pretty expressive way of saying that, maybe too expressive, because if you have a big access matrix like this, especially one where you could create new domains and new objects, it starts to get hard to answer questions about, well, who could acquire what access rights? Like we might ask, well, if you're in domain D1, can you write to object O1? Well, it doesn't say that you can, so you can't, at least not at the outset. But if you're running in domain D1, it looks like you could switch to domain D2, and you still can't write to this object, but from D2, you could switch to domain D3, and now you're the owner of that object. So you could give D1 the ability to write to O1 and then drop all the way back to D1, and then you could write to that object. So with an expressive way of talking about permissions, the more expressive you make that, the harder it gets to answer questions about what processes might be able to do. In general, questions like this, could this process gain the right to do so-and-so? Those are called confinement problem questions. And with a sufficiently expressive way of describing permissions, some of those problems end up being computationally undecidable. You could make problems that are so hard that you don't know what programs might be able to do. We've been describing access rights as if we're really going to build an access matrix or as if the OS is going to do that. But it's not really going to use a giant table to represent all of the access rights. Like I've said, it would be huge, and most of the spaces would probably be empty. If I just picked a random object and a random domain, and I said, what can this domain do with this object? The answer would often be nothing, or it would be same thing as everyone else. Maybe everyone can send jobs to a particular printer. If those are what your access rights are like, if that matrix would be a big matrix that's either sparse or has a bunch of the same entries within a particular column, an access matrix is a bad way to represent that, which is why we have these other three alternatives for representing that. Access lists, capability lists, and lock and key are mechanisms, or at least ideas, that show up in practical representations of permissions. Let's talk about access list first. I think of that as being probably one of the most common techniques you're going to see. Instead of storing all of the access rights in one big table, let's store them by object. So the objects are the columns. Instead of storing rows and columns, let's just store what's in each column, like I'm showing here. So object O1 has a list of everyone who can access that object, along with the access rights they have. O2, well, looking at the table, D2 can write to object O2 and D3 can read and write. So that's what I listed. Same kind of thing for O3 and O4. Well, this is a tiny table, so you might not notice it, but the advantage of this technique is if I've got a bunch of empty cells, I can leave them out of this representation entirely. So if your access matrix was mostly empty, this saves a lot of that storage. You don't have to store cells that are going to be empty anyway. And it also gives you a way of representing default privileges. I don't have this in this example, but let's say object O4 was a printer. And instead of saying, well, domain D1 and D3 and D4 can print to the printer, if you wanted to say, well, unless I tell you otherwise, everyone can print to this printer, you could just represent that as, well, you'd need a special notation for it, but some kind of default access permissions associated with an object. So this gives you a way of storing that. I guess another way you could go, if access lists try to save space by storing the access rights a column at a time, capability lists do the same thing, storing them a row at a time. Instead of telling me what can be done with each object, they say what can be done if you're running in a particular domain. So starting with the same access matrix, this is what it would look like as a capability list representation. So this top row, for instance, says everything you can do if you're running in domain D1. So just like access lists, this saves space if most of your table is empty. It's a little bit tricky because, well, backing up for an access list, it's clear that if I'm supporting owners of an object, then owners get to decide what goes in the access list for that object, who can access that. But not so for capability lists. You don't get to decide what goes on your capability list. If you could just add everything to it. So for this to make sense, owners of those objects, or people who could give away access rights for those objects, would decide what went on your list. So the OS would have to give us a way of modifying adding and removing particular access rights to other capability lists. Access lists represents permissions an object or by object. Capability list represents them by row, by domain. Lock and key kind of combines these two techniques. They take access rights in the access matrix and they associate those with a particular key. So that might be a group of users. It might be a little bit of cryptographic information that's generated for that object. Here, I'm just going to use smallish integers. So let's say I make up the key 25. And I use that to say, oh, maybe you can do something with these two objects. So for each of the objects, I'll have a list of keys. So a list of these numbers here, just 25 so far. And for each of those, it'll say what you can do with that object. So if you've got key 25, it lets you write to object 02, and it makes you the owner of object 01. So I've got what look kind of like access lists, but instead of saying what different domains can access that object, they say what you can do if you have a particular key. And then I'm also going to have a list for each domain that lists the keys that that domain can use. So if you're running in domain D3, it looks like, well, you got key 25, so you're the owner of object 01, and you can write to object 02. Up here, I put green boxes around that part of the access matrix because that's kind of the part I've taken care of so far. I've represented this, but I got a bunch more stuff that I need to represent if I'm just going to use lock and key. So let's give out some more keys. Maybe I'll give out a key 9000 that says you can print to the printer. I gave that to, well, if I wanted to do the same thing as this matrix, seems like I need to give that to everyone except domain D2. So that's what I did. And then I put an access right of print connected to that key 9000 on the list for object 04. So that takes care of these 4 items. Continuing, I'll give out write access for object 02, and I'll stamp it with just a random key I made up, 5566. And well, it looks like I could give that to these 2 domains, and that would let them write to object 02. Domain D3 already could write to that object, so I didn't really have to give it this key, but there's an advantage to giving out keys that give you rights, maybe rights that you already had, because it means there are kind of 2 reasons why domain D3 can write to this object. These 2 keys. If we later revoked one of these keys, like maybe that key represents they can write to this object because they're enrolled in this particular class right now. At the end of the semester, we could revoke this key. Maybe that class ended, so no one else, or we shouldn't be able to use that key anymore. But maybe they've got another reason why they can access that resource. So they could still access it using keys that we haven't revoked yet. So for lock and key, the nice thing is you could think of each key as having a reason that you've used it and a reason that you gave it out. And then you could revoke that key when that reason no longer applies. Continuing, I could give out, well, I went ahead and jumped ahead here. I'm giving out a bunch of different keys to my domains. I'm associating those with access rights on my objects. And unless I made a mistake, I think this should represent the same thing as what you have in this matrix. But obviously here, there are a bunch of different ways I could have keyed these access rights. I could have broken them up into different groups and given them out in different ways. And depending upon how I do that, that's going to make it easier or harder to revoke access to particular groups of users. Now, each of these representations has some advantages. Access lists are, well, they're nice because if you just want to check to see if a user can access an object, you just have to check the list for that object. The owner of that object obviously has control of what's on that list. It's harder to answer questions about what a particular domain can do. Capability lists are really easy for answering that. But I find often you don't need to ask questions like, well, what are all of the access rights I have? Often it's more important to say real fast, can this process access this object? And both of these representations are pretty good at that. There should be a hopefully short list you have to check to see if the access right you want is on that list. For access list, it's a list associated with the object. For capability list, it's associated with the domain. For lock and key, well, I might have to do a little bit more work. I got to look on the list for the object, and I got to look on the list for the domain and see if there's a matching key that lets me use the access right I want. But hopefully these are two short lists, so it shouldn't be too much computational work to find a matching key if one exists, especially again if those lists are short. And like we said, if you plan ahead, you can give it access rights in a way that gives you good options for how to revoke those access rights in the future. If you look at a Unix system and its way of storing permissions, I think by today's standards, the standard Unix mechanisms for permissions are some of the simplest you're going to find. But I think you'll see a lot of the stuff that we were just talking about. For things like files or shared memory segments or semaphores, Unix uses a permissions mechanism that's kind of made, at least the standard baseline permissions mechanism for Unix, is kind of made to use a fixed amount of storage overhead. For every object, they store a small number that's the user ID of the owner of that object. And, this typically might be a 16-bit number. So that's 2 bytes for that keeps up with the user who owns the object. Every object also has a group associated with it, a group owner for the object. And if we use the same trick for groups, that's 16 more bits there. And then they've got 16 bits after that. So far we're up to 6 bits. Those last 16 bits, oh, sorry, I said that wrong. So far we're up to 6 bytes. So 2 bytes for the owner, 2 bytes for the group, and 16 more bits. So that's 2 more bytes for what we'll call mode bits. And the mode bits say what you can do with that object. So they're kind of the list of access rights you can exercise. Those bits, well, it's 16 bits, but if you look at the low order 9 bits, they come in groups of 3, and that's what I'm showing at the bottom of this slide. The lowest order 3 bits are they represent read, write, and execute permissions for users that aren't the owner of the object and aren't in the same group as the object. So I think of them as other users. They don't have any special connection to the object. Any permissions that you give away with these 3 bits are permissions that can be exercised by other users. So they're kind of like default permissions. There's a bit for execute. So for a file, at least, you could mark it as executable. And if you do that with these bottom 3 bits, any user on the system could execute that file. There's a write bit, same here. If you mark an object as writable by other users, then I said this wrong a moment ago, but I'll say anyone who's not the owner or the group associated with the file will be able to write to that. Same thing with the read bit. So there are 3 bits that determine what other users can do. There are 3 bits that say, well, if you're in the same group as this file, then here's what you can do. Can you read the file? Can you write to it? Can you execute it? And then the next 3 bits say what the owner of the object can do. And normally you'll give more permissions to the owner than members of that group, and you might give more permissions to other members of that group than you do to other users. But you wouldn't have to do it this way. You could actually use some of these tricks to restrict access to an object for a particular set of users. So whether it's a file or a directory or a socket, or a semaphore, you've got these permissions that say what you can do with them, with that thing. But for different types of objects, these same bits are used to mean slightly different things. Like for a directory, you've still got these same 9 bits, but they're used to mean slightly different things. The read bit says whether or not you can get a directory listing. The write bit says whether or not you can modify that directory. So can you add or remove stuff in that directory? And the execute bit means, can you see attributes of stuff in that directory? So can you know things like the size of those things or who the owner of something in the directory is? So these same bits, we talked about this about a week ago, those same bits do different jobs depending upon what they're attached to. So here I'm showing what you might do with permissions. Here you might have, so each of these bits is, well, they're a bit, so they're 1 or 0. If that bit is set, if it's 1, that means you have that access right. If it's 0, it means you don't. And this example is kind of what I'm showing before. It looks like if these were the 9 bits on an object, then the owner could read and write that object, but not execute it. So could other users. But if you're not the owner and you're in the same group as the object, you can only read from it. You can't write to it. So here I'm using the group to mark users that don't have as many permissions, at least not for this object. This group part kind of works like a lock and key mechanism for Unix. This owner only applies to one user. Other applies to every other user on the system, but for group, you can generally pick who's in what group, and users or domains can be in multiple groups. So the groups you're in are kind of like the set of keys you have access to. Every object only has one group, so it's kind of like saying the list of keys for every object is easy to work with because it can only have one element on it. But these group permissions bits decide what users that are in this particular group, what they can do with that object. So again, this is kind of like a lock and key mechanism where objects can only have one key, but domains can have a whole list of keys for group membership that they can exercise. And I kind of skipped past the first part of this slide. I said it as I was talking, but I should say when I'm trying to check permissions, first the OS checks to see if you're the owner. And if so, these 3 bits determine what you can do. If you're not the owner, but you're a member of the same group, these 3 bits determine what you can do. If you're not a member of the group and you're not the owner, then these 3 bits determine what you can do. And that policy of saying, check these 3, or these 3 if you're a member of the group, or these 3 if you're not a member of the group, that lets you use these middle bits, kind of like a lock and key mechanism. For adjusting these permissions, well, there are shell commands that let you modify these mode bits. There's you may be familiar with chmod, that expects an octal number that just lets you, at least if you're the owner, lets you set these 9 bits. Octal is nice for this job because every digit of octal is 3 bits. So that would mean this 7 says what the owner can do, this 5 says what the group can do, and this 0, I'm turning off all the bits, says what other users can do. The chmod command also supports a friendlier syntax that lets you add and remove rights to particular groups of users. There's also a change ownership command that lets you, at least if you're the administrator, lets you move files or other things between different users. And if you wanted to see what the permissions are, ls-l shows you that. When you get a directory, a long directory listing, this weird looking stuff at the front, those are those bits. This is the owner of this particular file, and this is the group ownership of the file. So it's in the staff group. Well, these are just shell commands that lets you access the permissions information. Underneath these commands, well, they're just regular programs like we could write. They must be making system calls to do this. And that's what I'm showing here. There's a system call chmod or fchmod that lets you change the permissions on a file that you already have open, at least if you're the owner of that file. If you're the administrator, you can change the ownership of a file by calling fchangeOwner. And there are actually several versions of the stat system call that give you information about a file. So this tells you, along with a bunch of other stuff, what the mode bits and who the owner is and who the group ownership of a file is. These 9 bits we've been talking about are probably the most common permissions bits you might use, but really there are 16 bits there. What happens with the rest of the bits? Well, the next 3 bits are special bits that they do control permissions, at least some of them. I've shown at the bottom what these are normally called. The next 3 bits to the left of the owner permissions bits are the set UID bit, the set group ID bit, and what's often called the sticky bit. The sticky bit, it's probably the simplest one to talk about. In the early days of Unix systems, if you had an executable that got used a whole lot, the sticky bit was a way of telling the OS to keep it in memory after it's been loaded. Common shell commands might be marked with this bit. Things like your text editor might be marked with this bit as a hint to the OS that even if no one's using this program right now, you probably want to keep it in memory because someone may want to use it soon in the future. So this let you kind of tell the OS what it wanted, what you thought it wanted to cache. That bit is still there, but it doesn't necessarily get used for that job anymore. The OS can do a pretty good job deciding how to spend its memory and deciding what to throw out and what to keep in memory, even if no one's using it right now. So OSs don't generally respect that anymore. They might use that same bit for a different job. But these next 2 bits are still used for their original purpose. The set UID bit is kind of a way of temporarily changing permissions. If you run a program that has the set UID bit set, while you're running that program, it'll temporarily give you the rights of the owner of that program, or at least for the execution of that program. Set GID is the same idea. It'll temporarily give you group membership of whatever the group of that file is. And this is really a kind of a crude way of letting processes change domains. It's the thing we were talking about when we were talking about the need to put the switch access right in the access matrix to let programs temporarily lower or elevate their privileges. And this kind of gives you a way of doing this. You have to do it at the boundary of starting a new program, at least for what this mechanism gives you. You can't just say partway through execution, give me more rights. To do that, you have to go run a different program. And since you're running a different program, you don't really get to decide what that program does. It does whatever the code for that program does. But it means we can write programs that let you temporarily get privileges you wouldn't have, but just for the duration of that program, just while that program is doing its job. And if you look around standard system utilities, you'll find some that need this in order to do their job. While you're running that program, you temporarily get to do things that you couldn't otherwise do. For implementing these kind of programs, if you were coding one of them up, you have to be very careful that you don't have any security vulnerabilities. Because if I wrote a program that let you do things you couldn't normally do, and I had a vulnerability that let you break the program or get it to do stuff it wasn't designed to do, you could trick it into doing things that gave you privileges I didn't plan for you to have. So backing up, this is a crude way of letting processes switch domains. How do processes get domains in the first place? Well, I've kind of slipped up and said this as I've been talking through it. Usually, a domain is associated with a user of a computer system. Maybe that's a user like my user ID on a Unix machine, or maybe it's a user ID that's not really associated with a human user. Maybe it's associated with software that's been installed. But usually the same mechanism that's used to set up users on a system, that's the same thing that's used to decide what domain you're running in. Normally, sorry, I'm looking at my slide here. Normally, when a process runs, it runs in the same domain as the person who started it, which means a program gets all of the power you have as long as you're the one who started it. This is kind of how a Trojan horse worked. We talked about that a moment ago. If I can trick you into running a program, then as long as that program is running and you started it, it's as good as you on the system. It has your permissions. I might want to be careful about how I create domains and the permissions I give out to those domains, especially if those domains are what I'm going to use to assign permissions to a program. People usually use the phrase principle of least privilege to remind us that a running program should probably have as few permissions as possible to do the job that it needs to do. That, said like that, that usually sounds pretty obvious. Why would you give a program more than permissions than it absolutely needed? Well, we kind of just talked about that. If our permissions are just associated with users, then whenever you run a program, it gets the same permissions as you, even if you didn't want to give it rights to do everything that you do. So we kind of violate this principle all the time. Maybe a better example would be, I made up an example here. Let's say I want to work with a colleague in the department, and I want a server that can, let's say we're working on a shared project, and I want to be able to let others access files in the project. So we're working on this together. So maybe those are some of my files and also some of my colleagues' files. How do I run a server that can access both of our files? Well, I've got some choices here. I could take those files and I could just set their other permissions so that anyone could access them. And then the server could access them because everyone could access them. But to do that, I kind of ended up giving out permissions that I shouldn't have. I only wanted the server to be able to access those files, but I gave it access to all of them by just letting everyone have access to all of them. So I'd say I'm giving out more permissions than I should. I'm violating the principle of least privilege. How about if we keep the files the same and we just give the server more privileges? I could run that server as administrator, and then it could access all of my files and all of my colleagues' files and all other files on the system. That's probably giving out too much permissions to the program, to the server that needs to access these files. Is there some compromise I could do? Well, at least if I was on a Unix machine, it seems like that group mechanism would let me compromise on this, but I might need to make a new group. How about if I make a group that's just associated with this project? So myself and my colleague could both be in that group, and any files that we make that are associated with this project, we could mark them with that group ownership. And then when I run that server, I could let it run as a member of that group. And then it could access just those files, but I wouldn't have to give it way more permissions than it needs. And I wouldn't have to give away those files to everyone. Only that server would have privileged access to those files. In terms of the principle of least privilege, I would say that last example is the best solution of these three. Let's make a new domain, a new group that lets us give out the access rights we need to just this process. As processes run, we've noticed we might want them to be able to change permissions, to temporarily get more permissions to do stuff that they need to, or temporarily lower permissions if they're going to run code that's less trusted. If a process can change permissions as it runs, we'd say it has a dynamic assignment to the domain it's running in. If it's stuck in a particular domain, if it's stuck with a particular set of permissions, we would say its domain is statically assigned. And at least if you believe some of the stuff I said on the previous slide, it's probably good to let processes change domain as they run to handle, to do a good job of following the principle of least privilege. So that would mean I would need some way in my program, if it's running one big program, of saying, oh, it's okay to do this here, you can't do this here, of assigning permissions within the code. We'd call that a language-based protection mechanism. I'd want to be able to say things like, well, what code can call other code, what it can do when it's running within that code, what it can access. And we do have some mechanisms for this. From Java, you'll remember, I've got at least some way of marking functions as accessible only within a particular class, or sorry, methods, or fields as only accessible within a class, or accessible within other code from other code in the same package, or from any other code in the whole program. And that gives us some limited way of saying who can do what. I'll mention C++. A lot of object-oriented languages have similar mechanisms. I know you really haven't covered C++, so this part's probably not that interesting to you, but in C++, these are compile time mechanisms, and a clever programmer could get around the public, protected, private restrictions in C++, but not really in Java. Java is pretty uptight about this. And even if you were willing to hand code Java bytecode that tried to sneak around the access restrictions, Java would catch you trying to do this. Every time it loads in new Java bytecode, it does bytecode verification to make sure that no code is able to access fields or methods that it shouldn't have the right to access. So Java does have some language-based protection mechanisms that can be trusted, that you can't sneak around like you could in a language like C. The problem is they're not usually enough for what we want to be able to do. Consider how, well, you've got a file class, and it's got a public constructor that lets you open any file, and there's a scanner class that has a public constructor that lets you give it, I think, any input stream, which means you could write code like this that opened a new scanner that could read from a file like your bash history file. Bash history, every time you type a command, it gets recorded in a file that has a list of all your the last, say, 500 of your previous commands. Not really because the system's spying on you, but when you go back through your command history and you rerun old commands, this makes it so that works even if you log out and then log back in. There's a history that lasts longer than any one terminal session. So that's handy to me, but I wouldn't want untrusted code to be peeking around at my bash history, not necessarily because there's anything sneaky there, but maybe I typed some commands or I was looking in directories that I don't want untrusted users knowing about. I don't want them, maybe I put a command line option on one of those commands that I don't want an attacker to be able to see. But public, protected, private isn't going to prevent this in Java. All the stuff I'm showing here, these are public methods. So in Java, where we're already doing a pretty good job of deciding what code can do what, we still need more to say things like, well, opening a file, only certain code can do that. Java has a way of doing this as well. It has a way of marking code as being more or less trusted. And whenever you're going to do an action that requires trusted code, Java checks to make sure that action is permitted. And it does it by looking at what code invoked that action. So Java, like I said, it marks code as more or less trusted, based in part on where that code came from. Code that came off of your own local hard disk is marked, maybe if it's part of your installation of the Java runtime environment, it'll be marked as trusted. Code that you downloaded from the internet as an application was running, if you brought in additional code, that code can still run, but it's not going to have the same privileges, or at least it's not going to be trusted as much as code that came from your own local disk. So whenever you execute an action that you might not want to let everyone do, we'll call that a protected action. Java has a way of looking back and seeing who asked for that action. So essentially, who called the method to do that? And the idea is we only want to, there's some actions like opening an arbitrary file that we only want trusted code to be able to do. But like I'm showing this picture, it may be complicated. You may want to look back further than just the most immediate caller. If I've got something like opening a file in my file system, well, maybe that was called by some trusted code, and that was called by some trusted code, but maybe that was called by some untrusted code. Should I let it open that file, or is it really this untrusted code that's asking me to open it? Well, it kind of depends on what these functions are doing. If this untrusted code is trying to open an arbitrary file that it picked, like your bash history file, I might want to say no. But let's say it's just trying to open a maybe a configuration file or a preferences file that it created the last time it was running. Maybe I'd like to be able to provide that untrusted code with a mechanism that lets it do these protected operations, but only under particular circumstances that I get to pick, or really that this code gets to pick. And that's really what Java has provided. It provides a way of marking a call to a function as privileged, so that that call can be made even by untrusted code. That call can execute a protected action, and that protected action can look back up the stack. I got a picture here that shows kind of how you can think about this. It can look back up the stack and see if there's any trusted code that's willing to take responsibility for that action. That would let us create software mechanisms where even untrusted code could indirectly do protected actions. We're not just going to say no just because some untrusted code indirectly made this call. We'll look to see if there's some trusted code that's willing to take responsibility for that action. And if so, then the protected action can go ahead and execute. This would let us give away the ability to do this protected action, but only in particular circumstances, only if you do it through an interface that's well-defined and that's willing to do this, that's willing to say, oh, if they're going through me as the interface, I promise they're not doing anything sneaky. They're trying to open a file, but it's a file that I picked, not one that this untrusted code got to pick. And this, at least within Java, is a way of letting us track permissions, not just when we go to the OS and make a system call, but within a running program as it executes. And that gets us through all of our material on protection and permissions, on protection and security. We kind of jumped around a little bit. We started talking about the kinds of mechanisms protection gives us, and then we ran ahead and covered all the security stuff, and then we ran back and finished up the protection stuff. We just got a couple of chapters left. Let's go ahead and call it a lecture here, and then we'll start with talking about secondary storage next time. I'll see you then.